Hello everyone, welcome to TechSD, and today I'm going to show you how I created a device that can automatically control the universal induction cooker motherboard. The universal induction cooker motherboard is widely available in the market in very cheap cost. So you can see a custom controller card attached here, and this card is normally manual. It has a chip on it and it also has a 7 segment display. The display is used for showing the information from the induction cooker, and you can see the keypads also here. My requirement was to create a device that should automatically control the motherboard, not like manual in the controller card that comes with it. It is running a timer here in the video, you can see clearly. In this video, I am going to show you how I created this device and identified its communication protocols. Let's get started. To solve the problem, I inspected the motherboard microcontroller and the level was 18A. I searched that microcontroller level in the internet, but without any log, I could not find any information about it. I tried another one and still same. That's why I took its controller card and I inspected it. The controller card had some keys and display. That's why I suspected the chip inside it is something that controls these things. For that, I needed to find the dataset. So I tried to inspect it model and the chip was written something like AIP1628. That's why I went to the internet, I downloaded the dataset. The dataset was written in Chinese language, but I could use Google Translate to translate it. That's why it looks like AIP1628 and some descriptions were written there. I selected the text and I searched in the internet for translating it. Google Translate translated the chip details. This is a LED controller and keypad scanning chip. So the same chip can do the two things. One displaying the 7 segment display or driving the 7 segment display or getting the keypad scanning data. For communication protocol, I went to the timing diagram page. It has 3 pins STB, CLK and TIO. As the pin looks like the I2C protocol, but because of 3 pins, I said it is not I2C protocol. And this is custom protocol implemented by its chip manufacturer. That's why the communication protocol looked like that. STB became low, then after clock pulse started and each clock pulse rising phase, the bit is read. This is how communication happens. I also identified its keypad scanning things. For keypad scanning and sending the data, it needed 5 bytes to be sent to the microcontroller board. So each key has a certain byte. So we can say there will be altogether 20 keys supported. For power on off button for my motherboard, the K2 and KS2 were used. For that, I needed to set B4 bit high and send that bit, making it high on first byte. This is how I thought it should work. I kept scrolling to another page and where I saw the protocol implementation diagram is clearly written. As communication starts, STB should be low and clock pulse starts. In each clock pulse, there is a rising edge and that time we needed to read the beat. So after finishing reading all the beats, the STB becomes high. After that, we collect all the bits and form a byte, and from these bytes, we form whether the command is there or what data is coming through the microcontroller or to be sent to the microcontroller. From this dataset, I got enough information about the protocol and I started first prototype. I took the breadboard and made the wiring on it using the development board. The next phase was to write the code for the microcontroller. I wrote the C equivalent code and handled the communication logic properly. Now it's time to flash the actual software code into the microcontroller, and it went successful. Then I started testing the device with a real induction cooker motherboard. The initial testing was failed and I identified the problem using the oscilloscope. After finding proper timing, it went successful. The next phase was PCB design. I preferred small sized PCB, that's why I prefer the assembly based design. The PCB was double-sided and put few components on it. I preferred panelizing, that's why I made it very small as much as possible. After designing the PCB, I inspected it in a 3D view. The 3D view was so nice. I use rotary encoder here because I wanted to navigate the options so easily. Then I connected this with the real induction cooker impressive 3D view power on. I wanted to make was fine PCB at home. I'm pressing the key, and for that reason the timer printed that PCB on the paper. After doing the etching process and making the PCB at home, the first version looked like this. I was satisfied with the result. Then after I started assembling the component on it. After assembly, I got the final look like this. Now it's time to program the board. I put some header pins over there and flash the firmware perfectly in the first attempt. The screen shows how I flashed the firmware on it. Everything went successful. So everything went successful, and finally we learned how to handle or reverse engineer some protocols and communication pattern of induction cooker motherboard. Please subscribe our channel and thank you for watching. We'll keep posting similar videos in the future. Bye bye.